In this section, we're going to talk about batteries. We are going to define how battery works, what is the meaning of the voltage of a battery, and how to find and calculate what is the internal energy of a battery. The image on the right shows a battery, like a big AA battery here, connected to a light bulb through two wires. A battery is composed of three main elements. There is an electrolyte, which is a gel or a liquid. And in this electrolyte, there are two metallic plates immersed in it. One of them is the cathode at the positive terminal, and the other is the anode at the negative terminal. Anode and cathode use two different metals, depending on the specific battery. Now, chemical reactions occurs between the cathode, the anode, and the electrolyte, and the net result of that is that you can imagine a buildup of electrons where the anode is, and a shortage of electrons where the cathode is. The fact that there is a buildup of electrons at the anode generates an electric field inside the battery. The electric field will have this direction, so it's going from positive charges to negative charges. This will also means that the electrons will want to go towards the anode. This is easy to understand because if you think about it, the electrons are a bunch of particles with a negative charge. For some reason, a chemical reaction, they ended up being bunched up into a little area, but they don't really want to be close to each other because they are negative charges. They really want to go as far as possible from each other. Unfortunately, the electrolyte not only generated the initial chemical reaction that caused the buildup, but now prevents the electron from going from the anode to the cathode. So when you have a battery that is not connected to a circuit, there's really nothing to do for the electrons but to stay there. When you connect a circuit to the battery and you close the loop, you are giving the electrons an alternative path to reach the cathode. Now that the circuit is connected to the battery, the electrons have a way to reach the cathode, and one by one they will go along the wire, they will go through the light bulb. The light bulb hopefully will emit some light, and eventually they will reach the cathode. When there's no buildup of electrons at the atom anymore, the battery has electrons that are uniformly distributed. There won't be anymore any electric field within the battery. There won't be electric potential energy between the battery. And that simply means that no net work can be done on electrons, which also means the electrons don't really want to move from where they are. So even if you connect the battery to your circuit, you will not have any movement of electrons. One thing that I want to highlight here is that despite the fact that the electrons go from the anode to the cathode, because they are negative charges, the conventional direction of the current will be the opposite of the movement of the electrons. So the current will be assumed to be positive and going down from the cathode to the anode. Let's continue to analyze the example of the battery connected to the light bulb. If this battery is an AA battery, that means that we have a difference of potential equal to 1.5 volt between the two terminals. What does it mean? As we discussed before, voltage is the electric potential energy per unit of charge, and it's measured in volt. So that simply means that for each electron that goes from the anode to the cathode, the battery will have to do some work to push the electron across the circuit. And the work that the battery will have to do, it is equal to what's calculated by this equation, which is 1.5 volt multiplied by the charge of the electron. Because the energy per unit of charge is 1.5, so if you multiply by the charge of one electron, then you get the energy that is spent on that electron to make the electron go from the anode to the cathode. The final value is quite small, 2.4 multiplied by 10 to the minus 19 joule. Now, an AA battery could have about 10,000 joule of energy. That means that it can move a certain number of electrons before completely discharging. And calculating the number of electrons, it's quite simple. We just divide 10,000 joule divided by the energy of one electron, and we get that the total number of electrons that can be moved by this battery is equal to 4 followed by 22 electrons. Because voltage is potential energy per unit of charge, it is also defined plus or minus an arbitrary constant. For example, if we call this node A and this node is called B, all I can say is that VA minus VB is equal to 1.5 volts. So the voltage at VA minus the voltage at VB is equal to 1.5 volt. But the value of the voltage at A and the value of the voltage at B could be any combination of numbers whose difference is 1.5 volt. Usually, to make things simpler, the node of the two that has a lower potential is assigned with a voltage equal to 0 volt. So usually VB in this example will have 0 volt, and as a consequence VA will be equal to 1.5 volt. The node that is at 0 volt, in this case B, is usually called ground, indicated with G and D as well. And most of the time the circuits will also have a special symbol to indicate this node, and this symbol could be looking something like this, just like a triangle hanging from a wire, or something like this. These symbols imply that that point, that node, is physically connected to the earth, to the ground, under your house, for example. The reality is that it's not true most of the time. Think about a mobile phone. It's definitely not connected to anything. It is a standalone device. But the symbol is used nonetheless to indicate that that node is the node considered to be a 0 volt. In the previous example, I mentioned that an AA battery can have an internal energy equal to 10,000 joule. While you're probably familiar with the fact that the AA battery is a 1.5 volt battery, you probably never heard any amount of energy in joule specified for the battery.